So welcome in everybody to our next N3AS seminar of the lovely spring semester. And today we're excited to hear from Professor Jeremy Holt from Texas A&M University, who will be telling us about some recent progress in neutrino scattering and absorption in warm, dense matter. Please, Jeremy, take it away.
Okay, thanks a lot. Good afternoon. And thank you for this invitation to give a talk. So today, I want to focus on modeling neutrino opacities in warm and dense nuclear matter. And I also want to, before I go further, I want to highlight some collaborators, in particular, Young Shin and Ermal Rapai, who are some of the junior members of this collaboration. This work was also done with Sanjay Reddy. So I think probably all know that neutrinos are really a crucial participant both in core collapse supernovae and neutron star mergers. These the neutrinos they affect not only the hydrodynamic evolution of these systems, in particular the energy, the momentum, and the lepton number transport over relatively large distance scales. But then they also affect the composition of the matter that's ejected from these systems. And the composition, like for instance, the proton fraction, that's basically governed by charged current reactions that are converting protons into neutrons and vice versa through the absorption of electron neutrinos and antineutrinos. The composition of the ejected matter helps determine the nucleosynthesis outcome in these systems. And the present state of the art in terms of simulations is that we think core collapse supernovae, they might be the source of weak ARP process elements around mass number 90. That's kind of a best case scenario. But in order to get the strong ARP process, then we really need something like a neutron star merger event, which is a very large neutron fluxes. So not only the dynamical evolution of the system and the composition, but neutrinos are also one of the deepest probes of core collapse supernovae. And so we want to develop our neutrino modeling in such a way that with the next galactic supernova, we'll be able to make contact to experiments and help refine our models. So most of these effects are sensitive to the energies at which different flavors of neutrinos and antineutrinos decouple from the medium, whether it's the protoneutron star core, or whether it's kind of the accretion disk of neutron star mergers. So that's kind of what we need to understand, how the neutrino interactions with matter in these environments are affecting all of these different processes. So to give you an idea of what we might be able to learn from core collapse supernovae, we could just quickly zoom in and look at what are the key characteristics for neutrinos that are emitted at different timescales. So of course you have this initial neutrino burst from all of the neutrinos that are initially trapped in the infalling core. And then there's an accretion phase where we're basically trying to determine whether the core collapse supernova is going to succeed or fail. Okay, and in this case, we're very interested in the energy deposition of neutrinos behind the stalled shock wave to see in what scenarios they can provide that additional energy to re-energize the shock wave and lead to successful explosions. And then sort of the longer protoneutron star cooling period, which can last tens of seconds. Here we're going to be able to, with the next galactic supernova, we'll be able to study this time dependence of the neutrino energies. And again, we hope that that's going to, provide a probe of supernova mechanism to a better fidelity than what we presently have today. So there's many different, as you can see, many different processes, elastic scattering, reactions, pair production that are involved in core collapse supernova simulations and also neutron star mergers. But in this talk, I'm primarily going to be focused on neutrino nucleon elastic scattering and absorption. So these two different elements here. So the reason why I'm focusing on these is because to a large extent, they provide the largest opacities in this, the neutrino decoupling region, protoneutron star. And here, I basically show the different mean-free paths for these different neutrino elastic scattering shown in blue. So this is neutrinos on neutrons or antineutrinos on neutrons. You can see that those are both a large source of opacity, as well as these two red curves, which are the electron-neutrino absorption and the anti-neutrino absorption on protons. Okay, so as the neutrinos are propagating through the protoneutron star, they're undergoing a large number of reactions and collisions. And the region where they decouple from matter is what we call the neutrino sphere. And this just gives you a typical range of conditions where we expect the neutrino sphere to exist. So the temperature could be around 5 to 10 MeV, and the densities could be on the order of 10th, 100th, or even 1,000th of normal nuclear densities. But the matter is very neutron rich. Okay, and so we expect that the processes involving neutrons, both electron-neutrino scattering and electron-neutrino absorption on neutrons, to be some of the largest sources of opacity. And exactly where the neutrinos decouple from the region, that's going to set their energies. And the relative energy difference between electron neutrinos and antineutrinos is important for really a large number of different processes, including nucleosynthesis, flavor oscillations in core collapse supernovae. So that's what we want. We want a better understanding of these reaction processes and how they govern the final average energies of neutrinos and antineutrinos that are decoupling. So how we calculate these within a many-body framework is shown here. So the cross sections for neutrino nucleon scattering, basically shown here through the exchange of a neutral Z boson. So that involves various factors, as well as these structure functions, dynamic structure functions, for that basically encode correlations in the density and spin density. And for neutrino absorption, which is shown here, which proceeds through the exchange of charge bosons, then here we have to worry more about Pauli blocking effects for the final state lepton. But we also, at the end of the day, have to calculate these dynamical structure functions, which give us modifications between the in-medium cross-sections and the free space cross-sections. Okay, and of course, depending on the densities, the temperatures, these correlations can play an important role. So how we're going to calculate these within a many-body framework is relating them to the imaginary part of the density and spin response functions through the fluctuation dissipation theorem, where you basically need just the imaginary part of the density and spin correlation functions, and then as well as the detailed balance factor shown here. Okay, so how we can calculate these quantities diagrammatically is shown here. So this would be the 0th order contribution to the response function. And these diagrams show mean field corrections, right? So these are basically just affecting the propagation of the protons and the neutrons, which are shown here with the directed arrows. This wiggly line corresponds to the exchange of a W or a Z boson, but typically we're not going to resolve those features. So we're just thinking generically in terms of an energy and a momentum transferred to the medium. Okay, so here's, for instance, neutrino scattering goes off at some angle, and it transfers an energy omega and a momentum q to the medium. And generically, what's going to happen is we're just going to excite particle-hole pairs. Okay, so that's what these different loops represent. So in addition to these mean field effects, we also have the correlations, and these are included in the so-called vertex corrections. So this is just the first order mean field and the first order vertex corrections. Now, everything I've talked about up until now has been, oh, I see that Wick raised a hand.
Yeah, I just wanted to ask you, are there also corrections due to long range, if you're doing a vector current, for example, of photon exchanges that allow you to go through bubbles and propagate over long distances, things of this sort?
Oh yeah, sure. In principle, yeah. So we're not going to be including any of those effects at the moment. But yeah, something like coupling to photons and then
Yeah, plasma-like effect.
positron. Yeah.
Yeah.
Yeah,
Okay.
exactly. Right. So yeah, those effects, they can be important in certain regimes. But yeah, we're not going to focus on them in this particular talk. But yeah, good question. So yeah, we're primarily just going to be focusing on the interplay actually between these nuclear mean fields and nuclear correlations. So there are, like Wick said, there are electromagnetic processes that also enter, but we're primarily going to be interested in strong interaction effects in this talk. But as you could imagine, this is a very old problem. And people have attacked this, really since the early 1980s, Iwamoto and Pethick, and Sawyer. So there's a number of different ways that one can try to include corrections due to the nuclear force. So you can use mean field models, either SCRM or relativistic mean field models. You can devise a Fermi liquid description of nuclear matter, also the virial expansion. So all of these have certain strengths and certain weaknesses. So my particular approach is to study these effects using as microscopic approach as possible. So starting really from fundamental nuclear forces. The disadvantages is that typically the calculations become a little bit more challenging because microscopic forces, they have finite range. They're also non-local. They have strong tensor components. So just the form of the nuclear force is a lot more complicated compared to the more simplified treatments above. But I think ultimately that's where we want to get to, because that would lead to a better microscopic description where I think we have a better control of the uncertainties. Okay, so let's look at the role of mean fields. So of course, a nucleon propagating in a medium, it has both an effective mass and an energy shift generically. And so compared to the free spectrum shown here in black, then for a beta equilibrium system at sort of 1/10 saturation density and T equals 8 MeV, these are the mean fields, or the total neutron energy and proton energy as a function of momentum. Okay, so the energy momentum dispersion relation is modified. And effectively what that does is, since the proton-neutron interaction is stronger, then that leads to a much larger mean field for protons, shown here in red, compared to neutrons. Because after all, the medium is neutron-rich, and the proton-neutron interaction is stronger than the neutron-neutron interaction. Okay, so we're basically thinking of modifications to neutrino absorption along this line, where we've just dressed the neutron and the proton with mean fields. Now, the effect, if we look at, this is just the 0th order response function. When we include the effect of mean fields, what we see is that, really the distributions of the neutrons and the protons in the final state, they're not strongly affected. And that's just because to first order, you see these big energy shifts, but those energy shifts can be approximately absorbed just into a redefinition of the chemical potential. Okay, so we're basically fixing the matter density and temperature, and so we have to continually adjust the chemical potentials to match that. So to first order, I would say really nothing changes in the distribution functions for the neutrons and the protons when we're calculating the response function. For neutrino absorption, the primary effect is shown here in the denominator. So we want to extract the imaginary part of the response function, which is related to the dynamical structure functions. And so we're basically setting that denominator equal to 0. And so what we see is that generically, the energy at which these processes occur gets shifted by that mean field splitting between neutrons and protons. And so here we show a calculation of the imaginary part of the charged current density response function. So without including interactions, we have this blue dashed line, and then including a number of different microscopic interactions derived from chiral effective field theory. We have the green line, the red line, and then the black line. So we see, first of all, that there's actually a pretty large dependence just on the choice of nuclear interaction, and in particular, the choice of this resolution scale. We can get pretty large mean fields on the order of 10 MeV splitting, which, as you can see, it's basically just producing this shift in the response function to much smaller values of omega. How does this actually affect the cross-section? Well, notice that if omega is decreasing, then that's going to increase the final state electron energy, which is going to increase the absorption cross-section. And it's also going to push these final state electrons into a region where there's less Pauli blocking. Okay, so we generically would see that mean fields tend to enhance electron neutrino absorption. And for basically the opposite reasons, they would suppress electron neutrino absorption on protons. Okay, so without including any kind of nuclear correlations, we would have these dashed dotted lines for the inverse mean free path as a function of the neutrino energy. And generically, we see that mean fields are causing an increase in the cross sections and hence a decrease in the mean free path. So how does this affect simulations? Well, this shows, for instance, the luminosity of electron neutrinos and antineutrinos in a proto-neutron star cooling simulation. And so without mean fields, you see that the luminosities are much closer together. And that's because the neutrinos are decoupling around the same region. But when you include mean fields, then all of a sudden the electron neutrinos are decoupling much later, right? Because they undergo stronger reaction cross sections, and so they're just their energies as they come out are much reduced. Okay, and so you see that there's this large splitting between the antineutrinos, which have larger energy, they decouple earlier, and the electron neutrinos, which decouple later and hence have smaller average energies. This also affects the composition of the neutrino-driven wind. So again, without mean fields, you see that the ejected matter is proton-rich. But since we've basically enhanced the energy difference between neutrinos and antineutrinos, then the antineutrinos, since they have greater energies as they come out, they can convert more protons into neutrons, and hence you see that there are conditions that could be favorable for, say, a weak R process. Okay, the neutron fraction is larger. Okay, so those are some of the impacts of mean fields on simulations. One thing that you might notice here, if we're looking at the effect of mean fields from microscopic forces compared to phenomenological models, you see that in general, these microscopic models are kind of weak. Okay, so even this sort of the largest effect here with the N3LO 414 potential, which has the coarsest resolution scale, but the largest mean field shift, even that is much smaller compared to typical relativistic mean field models, and then what you might guess based on pseudo potentials derived from nucleon-nucleon scattering phase shifts. So that's kind of one of the challenges with taking a purely microscopic approach. In order to build up the physical mean field, you actually need to go to higher orders in perturbation theory. So one thing we've been looking at recently is to now evolve these potentials to lower and lower cutoff scales. So basically coarser and coarser resolution. And what we find when we take our realistic microscopic forces and evolve them to a lower resolution scale, we see that we can recover these large mean field splittings. Okay, so hopefully going forward, this is what we're going to be looking at in order to better mimic phenomenological models. Okay, and once we go to lower and lower cutoff scales, these microscopic forces become more and more perturbative. And so we're building all of the essential physics into that leading order mean field diagram. And this just shows like where we might choose that cutoff scale to be between roughly KF and maybe the square root of 2 times KF. Okay, so that's mean fields. Now we want to take a look at vertex corrections. These vertex corrections have been much less studied in the literature. There have been some efforts, but they definitely haven't received as much attention as mean fields. So our goal over the last few years was to develop a consistent scheme to calculate these vertex corrections. So they involve some complicated, multi-dimensional integrals. And one of the key features, though, compared to just mean fields, is that they involve off-shell matrix elements of the nuclear potential, which in some cases with the nuclear tensor force and one pion exchange can be quite large. So we expect these effects to be large. We want to see how they compare to mean fields. This just shows if we take that first order vertex correction, how just that first order correction compares to the mean field. So this is for the left columns are for neutral current processes. Okay, and the dotted line is basically the 0th order calculation with no mean fields. And then we see that, of course, for neutral currents, mean fields don't really do anything. That's because neutrons are they're just shifted identically. So mean fields don't really have much effect at all for neutral currents. And then when we look at the vertex correction shown here in green, we see that generically it's pretty small compared to the first order or the 0th order response function in the neutral current. Now, for the charged current, something rather interesting occurs. First of all, we've already seen the shift in the imaginary part of the response function. But then when we look at the first order vertex correction shown here in green, we see that the first order correction is basically on par with the 0th order correction in terms of its absolute magnitude. Okay, so that's already a little bit concerning because after all, we're doing this in perturbation theory. And if the first order correction is as strong as 0th order, then you might want to question your perturbation theory approach. As we'll see, though, I think this is actually a kind of a harmless feature, and I think it just occurs at first order in perturbation theory. Also, because those vertex corrections are so large, you can obtain unphysical regions in the dynamic structure function. Right, the structure function is related to the physical cross sections, and those can't be negative. But here you do see, because of that large interplay, you see these unphysical regions. So what we've been developing over the last couple of years is an approach that does, in fact, cure this problem, and it also cures the problem of this very large first order correction. So in particular, we've thought about resumming to all orders in these iterated bubble diagrams, the vertex corrections to neutral current and charged current response functions. In some cases, you can have nice analytical expressions for the response function. In particular, if you're looking at the RPA response function for mean field models or Fermi liquid theory, then you can develop these analytical equations. But for microscopic nuclear forces, which are non-local and finite range, we have to do something more involved. So on the one hand, what's nice about the RPA plus Hartree-Fock is that it's guaranteed to be a conserving approximation. And so that means you're going to have physical cross sections. You also obey some rules. All of the properties of the exact dynamical structure function are conserved in a certain set of approximations called these conserving approximations. In addition, the RPA can account for collective excitations. And as we'll see, these are particularly important in the charged current reaction channel. I won't go into a whole lot of details here, but basically what we have to do to solve the RPA equations is we first go through this vertex function. So for the vertex function, we can iterate that to all orders in this integral equation. We can extract the imaginary part by first discretizing this integral, rewriting it as a matrix equation, and then extracting the eigenvectors and eigenvalues. And again, I won't go into too many details, but we've worked out how to go through that process in order to construct the imaginary part of the RPA response function, which is now applicable to any arbitrary nucleon model of the nucleon-nucleon interaction. Since you've discretized the integral, you do have to introduce a smearing function in these delta functions. Okay, so we have a finite number rather than a continuum, but we've checked that that can always produce inexact results. So here are some results. So this is for the neutral current channel. This is the density dynamic structure function, and this is the spin density dynamic structure function. So we see that generically, under typical conditions for the neutrino sphere, the density structure function is enhanced from the blue up into the black when we include RPA correlations. And in the spin structure factor channel, we see that the spin response is reduced in this region. And that actually agrees pretty well with some earlier work done with pseudopotentials with Paolo, Sanjay, Srinivasan, and Neil Warrington. So they used again sort of a phase shift approach where they modeled the bare nucleon-nucleon interaction in terms of pseudopotentials defined by phase shifts. But they find the exact same thing: an enhancement in the vector channel and a suppression in the axial vector channel. What they couldn't do, though, is study the charge current reactions, because one of the problems of the pseudopotential approach is that if there's a large momentum transfer, then the framework breaks down. But we can handle that within our framework. And when we now look at the charge current reactions and the RPA corrections, then what we see, without RPA is shown here with these blue dotted and dashed lines for free and then mean fields. And then when we include the RPA, we see these very strong peaks. Okay, so this is indicative of nuclear collective excitations at these particular energies. Okay, and we're going to study now the role of these collective excitations, because it turns out that these collective modes have a really strong impact on the final cross sections. So if we look at the dynamic structure functions, or actually this is just the response functions, if we just had a non-interacting gas, the response function, we see it would be peaked right around omega equals 0. Mean fields, as we said, it shifts this to smaller energies. And so now actually the medium is giving our final state electron energy. But now when we include RPA correlations, we see that we went down from mean fields, and now when we include both consistently, so this is mean fields plus RPA, now we've actually shifted the strength to positive energies. Okay, so now we're actually giving energy to the medium, and that's going to result in a dramatic change in the neutrino and antineutrino absorption cross sections relative to just including mean fields alone. And basically the exact opposite happens in the anti-neutrino case. Okay, so what we would see then, if we now look at the differential cross section with respect to the outgoing electron energy in neutrino absorption. So we see the blue dotted line for just the non-interacting response function. When we include mean fields, we see that the primary effect is that we've increased the electron energy, and we've also broadened it just because of the greater phase space that's allowed now because of the energy shift. But when we include RPA and mean fields consistently, you see there's a dramatic roll, right? So the peak in the mean field gets reduced, and then we see this sharp peak, which is indicative of the role of collective modes in the differential cross section. Now, when we look at what happens to the inverse mean free path, so again, we studied a number of different microscopic nuclear forces shown with solid, well, basically lines of different intensity. So again, the blue is non-interacting nucleons, and including the effect of mean fields through different choices of the nuclear force. Again, it increases the absorption cross-section. But then you can see when we now include consistently RPA correlations, there's really a dramatic change relative to the free space mean free path. And at low energies, kind of like we discussed before, the exact opposite happens for the anti-neutrino absorption. So the presence of this collective mode, so this actually provides a new pathway for the conversion of electron antineutrinos into positrons. Okay, so normally that electron neutrino would have to elevate a proton, which is very deeply bound, into a neutron, which would require a lot of energy. But now there are basically these positively charged collective modes sitting in the system, and by coupling to those positive collective modes, the neutrino can undergo this type of process much more efficiently. Okay, so we see that there's an enhancement in the electron neutrino absorption cross-section at relatively low energies. Okay, so this is pretty interesting because the effects are exactly the opposite of mean fields. And at least in the case of these chiral potentials between 400 and 500 MeV, it appears that basically the effect of these collective modes and RPA correlations are kind of dominant. So other people in the context of mean field models have found something similar. Right, so in particular, without RPA corrections, those are these solid lines for the neutrino inverse mean free paths. And then when they include RPA correlations through these relativistic and non-relativistic mean field models, they also see a suppression in the inverse mean free path by again maybe a couple orders of magnitude. Again, one of the possible problems, though, of phenomenological models is that they observed these types of instabilities. So in the neutral current channel, it turns out that a lot of the phenomenological mean field models can have ferromagnetic instabilities, which, you know, we don't know for sure, but we kind of believe that those are artifacts of the mean field models. It's something still to be investigated. But that's, you know, one of the challenges of mean field models is that the spin, you know, the spin degrees of freedom are not as well constrained, and they can give rise to ferromagnetic instabilities, which we don't see in our microscopic calculations. So finally, I want to come back to the question of the scale dependence, right? I think this is really crucial because if we just go back, you know, if we're just using these nuclear forces at first order in perturbation theory, then, you know, we've generically seen that we can't get the mean field splitting strength that phenomenology gets. Okay, so we want to come back to this topic of what happens when we lower the resolution scale in order to produce nuclear forces that, you know, can better capture all of the mean field at leading order in perturbation theory. Okay, so this is this shows basically the peak. If we come back to this plot, so we see the peak in the response function at zero momentum transfer that basically identifies the location of the collective mode. And we want to see how this peak evolves with our choice of nuclear cutoff scale. So we see that if we don't include mean fields, so we're just looking at RPA correlations, then that peak goes to higher and higher energies. Okay, and that would basically mimic the effects that we see, that we've already seen. But then when we include RPA plus mean fields consistently, we see that the peak in our response functions are shifted to smaller and smaller energies. So what we've discussed up until now, you know, basically the peak in the response was at slightly positive energies, so somewhere around here. And if we were to evolve our interactions to smaller resolution scales where they're picking up more effects at leading order, then we see that, you know, kind of generically, the mean fields are winning, right? This is a trend that's going down. But but remember at this value of lambda equals KF, the mean field splitting was about 30 MeV, right? And so the effect of nuclear correlations, even though you're still in a negative energy regime, it's strongly increased the peak from about -30 up until about, say, -5 or -6. Okay, but again, this kind of gives us an estimate for the uncertainties in our calculation. So I think when we improve upon our microscopic modeling with these low momentum interactions, then I think the basic trends that we've seen before are going to be intact, but we're probably not going to see as large of shifts in both the case of the neutrino absorption and anti-neutrino absorption. So still a little bit of work to do there, but just kind of wrapping up, I think the main take-home message is that, well, we really need to include RPA correlations because they build up through these iterated bubble diagrams the effects of nuclear collective modes. And these collective modes, they strongly suppress electron neutrino absorption across all energy scales. And they enhance electron anti-neutrino absorption at low energies. And if you go to higher energies, they actually suppress the absorption. But in any case, I think it's clear that one absolutely has to treat both of these effects on equal footing. And in terms of where we need to go from our microscopic perspective, we need to evolve our potentials down to this lower cutoff scales so that we can accurately capture at leading order the nuclear many-body effects that traditionally need higher and higher orders in perturbation theory to generate. So with that, I'll stop and take any questions. Thank you.
Great, thank you, Jeremy. Do we have any questions for our speaker? I see a hand already from Susan. Please go ahead.
Thank you very much. It was very interesting to hear your talk. I wanted to ask about the instabilities you saw in, I guess, at somewhat higher density, and you remarked that they appear in an artifact of your phenomenological interaction because of poor understanding of the spin degrees of freedom. I mean the cuspy things, yes. So my question is, I do recall my colleagues Eppelbaum and Meisner being keenly interested in polarization observables in few body systems and chiral effective theory. So I'm thinking that there is some germane work in regards to spin-dependent interactions in this context. I just wanted to alert you to that, or maybe you have any comment why that isn't germane to your context. I just wanted to let you know. Thank you.
Yeah, thank you. So kind of two important features there. So the first is that, we are using chiral nuclear interactions. So, if they're able to constrain, some of the contact terms in chiral EFT with these spin observables, then that's great from the microscopic perspective, right? And that gets built in and fed through into all of the calculations that I'm working on. Notice these were not my results. Okay, so these were mean field calculations from some other collaborators.
Oh, sure, yeah.
But the other thing is that, unfortunately for these light nuclear systems, which is, what the Eppelbaum and collaborators are working on, unfortunately, those don't provide a good framework for constraining mean field models because typically, so that's kind of the issue there. I think it's, it's probably not going to solve that feature just because, they don't, it's not a microscopic framework. So they're typically fitting to kind of bulk properties rather than, say, scattering observables, spin observables.
Oh. Okay, very well. So the basic disconnect in the matter of the construction that these are the mean field models intrinsically. Yes. Okay.
Yeah. I mean, I'm not an expert in the mean field models, but as far as I know, they wouldn't be able to incorporate that very well. But well, maybe Zidu is.
So I would think you could imagine doing studying polarization observables in the context of a system for which mean field theory would be appropriate. And then one would think that you would maybe constrain some of these problems.
Oh, sure. Yeah, I think they do that to the best of their ability. Maybe Zidu, I don't know, Zidu, are you wanting to ask a add-on question to that, or is it independent?
Yeah, sure. Yeah, thank you for asking. So actually, those are our figures. Yeah, so usually that peak won't appear in the mean field calculations. So those peak appears for the RPA calculations. So those dashed curves are RPA plus the mean field calculations, but we didn't consider the vertex correction. And I guess, so actually, I mean, the appearance of this peak is due to a poor understanding of those Landau parameters. So as we can see here, those black dashed curves are coming from the UNIDAF equation of the states. And actually those UNIDAF equations of the states, they give not very well constrained G-primed Landau parameters. And those G-primed Landau parameter from the UNIDAF version equations of the state are very different from the others. And that a little bit exotic G-primed parameter from the UNIDAF is causing this kind of the peak. When we are fitting afterwards, when we are fitting our RPA calculations with a lattice chiral effective field theory, those peaks disappear, at least at the densities below saturation densities. Yeah, so that's what we observe. So anyway, to conclude is that if we have any observables that can guide our RPA calculation in the spin-dependent channel, then very likely those peaks below saturation density will disappear. So that's the conclusion, yeah.
Yeah, thanks, yeah.
Yeah, next I see a hand from Wick.
Yeah, I was just going to ask if we understand how this connects to what we know about neutrino reactions just off heavy but still finite nuclei. It's been known for a long time that if you put in RPA corrections, what they tend to do is they move the electroweak responses for both neutrinos and antineutrinos to higher energy. I mean, that's basically why the giant resonances are 20 MeV instead of at 10 or 12 MeV. So that would argue that that's qualitatively similar to what you have for the RPA, but then you have these big mean field effects as well. And I can't see any analog for those. I mean, after all, if you study neutrino responses in lead, then you're using somebody's effective interaction and it's been pretty carefully tuned. And so the standard physics of what the core of the nucleus is doing to the valence nucleons is incorporated into the calculations. But still, in the end, what you find is this movement of electroweak strength to higher energies. So have you thought about the problem from that viewpoint of why the nuclear matter might be different from why, in other words, why lead is not a good substitute for nuclear matter?
I haven't thought about that particular question, but my first my first impression is that in the supernova environment, it's really neutron rich. So the proton fraction is something like 10%. And so there, really, what you're interested in is not the overall mean field effects, but the mean field splitting. And so I would even in a heavy nucleus like lead, where the asymmetry is maybe like 20% neutron proton asymmetry. So I would suspect that the mean field effects would be smaller there because the splitting isn't as large as in a supernova medium. That would kind of be my first guess.
Yeah, that's an interesting way to think about it because the giant resonances do split as you begin to produce, neutron proton asymmetries in heavy nuclei. And so I wonder if you could relate this in some way. I mean, there ought to be a relationship, and at least the results seem, roughly consistent with what you would get from a heavy nucleus. Very interesting talk. Thanks a lot.
Thanks.
Do we have any more questions for Jeremy? Another hand from Zidu. Please go ahead.
Yeah. So yeah, thanks, Jeremy. I have maybe a kind of technical and detailed question. So I'm wondering, for your calculation of those structure factors for neutrinos and for anti-neutrinos, so what's the main difference of the structure factor for the neutrino and for the anti-neutrino? Do you just, switch the proton and the neutron indices in your calculations, or there are something more?
Yeah, basically. So if one goes to the, the expressions, oops, where is it? Oops. Yeah, right here. Yeah, right. So really the only difference is that all the neutrons change to protons and the protons change to neutrons. That's the only difference.
I see. So it is just because, the switch of these two isospin indices that is causing this kind of the very different effects on RPA. Is that right?
Oh, you mean from, okay.
Yeah, because you say that, the RPA is somehow decreasing the neutrino opacity, but increasing the anti-neutrino opacity. And that is due to the switch of these two indices.
Well, it's really due to
Maybe Sandra has something to say.
how we're coupling to these collective modes. So that's really, so these collective modes, they exist in the medium, and we can either excite them, sort of in the case of yeah, we're really interested in how the two processes are interacting with the collective mode. So I'm trying to think if I have a better right. So the electron neutrino, as you see, when we include the effects of RPA correlations, the response goes up to positive energy. So now that means we're actually giving energy to the system, right? Which I think, we should interpret as we're basically generating collective modes. You're exciting a collective mode at a very localized energy. So in the case of the antineutrinos, though, really what we're doing is we're taking a collective mode that's already sort of thermally populated, and that antineutrino is interacting with that sort of that collective mode that's already present in the system, and it's getting energy from that collective mode. Okay, so those collective modes are definitely, they're at much higher energies than, say, the typical protons in the medium, and it actually provides an avenue to go through this neutrino absorption process. So yeah, it all comes down to how we're interacting with the collective mode, because this collective mode is very sharply peaked, and so a lot of just the strength of the response gets localized in that region.
Okay. Well, yeah. Okay, but anyway, but in the detailed calculations, the differences between these two types of the structure is just the switch of the
Exactly.
and the,
Yeah, sorry if that was just your question. Sorry for the long-winded. Yeah, but you're literally just changing neutrons and protons.
I see. Okay, thank you.
I see a hand from Sanjay. Please go ahead.
Hi, Jeremy. Thanks for a very nice talk. I was intrigued by your discussion of the scale dependence at the very end, and I'm trying to understand that. So, the energy of the collective mode, that's a physical observable, right? That's just something that's, if you did the whole correct calculation, including all the non-perturbative effects, there's a number. Now, you're making some approximations, and then you want to vary the scale. And I would have thought there would be higher body operators that would come in to ensure that, the scale dependence is not there in the energy of the collective mode. So I'm trying to square away understanding of, we have a physical energy scale that we have to reproduce. And when you change the scale, there's got to be some new physics that, like an RG equation that says this cannot change.
Yeah, right. So there, I mean, there's not only an RG equation, but it's, you also have to include higher orders in perturbation theory.
Right. Okay.
So I think my interpretation is that, actually you see in the case of just the peak, sort of the location of the collective mode, it doesn't, it varies over 5 MeV. And that could be due to, I'm almost sure it's due to missing higher order perturbation theory contributions at these very large scales. A lot of interactions nowadays are kind of right around here, like 400, 500 MeV. Yeah, I mean, if you were to perform an exact perturbation theory calculation, then like you say, it should be scale independent. And you might, as you're doing the RG evolution, there might be some other operators that you'd have to worry about as well.
Yeah, I'm wondering what those operators are. Are there some, is it the 3-body force? Is there some other, interaction that we need to include, like a higher order in the momentum expansion?
Yeah, I don't have a good, so let's see if this is just. And so, I mean, in principle, when you do the RG evolution, you do have induced many body forces, but
Yeah.
for these low densities, I would expect those to be pretty small, the effects of any kind of many body force. And so, I mean, my first guess is that this lambda dependence is really due primarily to building in more physics at lower order using more perturbative interactions. And so if we were to do, I mean, I can't do it in this case, but I've definitely seen in the context of mean fields. I'm not sure if you were here at the very beginning of the talk, but we looked at this for mean fields. And definitely I've done calculations where if you look at first order and second order perturbation theory, then this relatively sharp rise in the mean field, it's much reduced just by including second order perturbation theory.
Okay. So yeah, you think that all of the scale dependence is just that you haven't included more diagrams, not because you've not included more operators.
That's my suspicion. If we were at higher densities, then I would actually think that probably there's missing induced many body forces. Yeah, but at these low densities, that's what I suspect.
Okay, thanks.
Any last questions for our speaker? I don't see any hands, so let's thank Jeremy again. And thank you all for joining us and for a great discussion.
Thank you.